Assalamualaikum and hi. My name is Siti Azia binti Azman. My matrix number is CE220097. Today I would like to presentation about our group presentation project. So our group is group 5 and our lecturer's name is Dr. Jaiz bin Yas. So this is our group members. First, Muhammad Shazwi bin Hisham, CE220004. The second one is me, Siti Azia binti Azman, CE220097. And the last one is Tisian King, CE210204. So let's proceed about our introduction. So for this assignment, we are assigned to design and simulate a third order band pass active filter using OP amplifier. An active filter consists of active element, which are transistor and operational amplifier, that is added with to passive element like resistor. So as we know, a third order band pass active filter is a type of electronic circuit that permits a certain frequency range to pass while alternating frequency outside of the range. It has a high selectivity and is widely employed in audio and signal processing application. So, a simple active band pass filter can be easily made considering together a single low pass filter, which is present on the right side with the high pass filter.
So, Assalamualaikum. I will present my part, which is a circuit diagram. So, as we can see, we use a 5 amplifier, which is a 741 amplifier. So, we have 6 capacitor and 16 various value of resistor that we use in this part. So, this is our circuit diagram, which is we construct in Proteus 8. So, from the result that we get, for frequency, low cut-off frequency, we got 1.13 kilohertz. So it's not a bit far away value from that as that we got from spec given. So which is a 1 kilohertz. So for high cut-off frequency, we got 9.05 kilohertz. For this high cut-off, we got a little bit far away from our spec given, which is spec given is 10 kilohertz. So I think maybe we have some problem that we will explain in conclusion and our discussion and conclusion. So, so for the manual calculation, we use to find a high cut of frequency, we use a formula that 1 over 2 pi RC equal to 10 kilohertz, that the spec given, which is a 10 kilohertz. So for R, we assume as a 10 kilohertz, 10 kilo ohm. So we substitute the value that we have to get a capacitor value, which is a 1 over 2 pi times 10k times 10k. So we got 1.59159 nanofarad, which is not far away from the actual value that we use in our circuit diagram, which is 1.5 nanofarad. For low cut-off frequency, we use 1 over 2 pi RC, also same formula for high cut-off. So the spec given is a 1 kilohertz, so we assume R as a 5 kilo ohms. So also substitute the value that we have into the formula, which is a 1 over 2 pi times 5k times 1k. So we got 31.83 nanofarad, which is not far away from our actual value also, which is a 33 nanofarad. So for mid gain, we can see here as our formula is a 20 log A. A is a mid gain, so we have a spec that given. We have spec given, which is a 80 for our mid gain. So we just substitute into the formula, which is a 20 log 80. So we get a 38.06 dB. So this one we are already plotting in our simulation result for our graph. So for FC, we can see square root FL times FH, which is a square root 1 kilohertz times 10 kilohertz. We got a 3.16 kilohertz. So for bandwidth, BW is FH minus FL. So 10 kilohertz minus 1 kilohertz. And then we got our bandwidth is 9 kilohertz, which is between a low pass and high pass graph in our ground. So for Q, we got a FC times BW. Sorry, FC over BW, which is a 3.16 kilo times 9K. So 0.3511. So I think that's all from me, which is a basic manual calculation we use for FH, FL, mid gain, and our FC bandwidth, also a Q. So that's all from me. Thank you very much.
Hi, I'm T, and I will continue to present about the testing result and the comparison between the theoretical result, simulation result, and the experimental result. First, we will set the function generator. The input voltage will be 350 milliwatt, and the frequency will be 4.9 hertz. And we will set the power supply to 15 volt for the positive VCC and the negative VCC. And this is our input. We connect to the function generator and the channel 1 of the oscilloscope. And this is our output, and we will connect to the channel 2 of the oscilloscope. And this is positive VCC, and this is ground, and here should be a jumper for the negative VCC. And okay, this is the testing result when we increasing the testing in, input frequency at from 0 to 1 kHz. You can see that our output of the voltage will be increasing, and when we see the frequency input frequency is around between 1 kHz and 10 kHz, you can see the output will be no increasing or decreasing because the gain is saturated, and we can see that the output voltage will be 27.7 volt, and the input frequency is the 350 millivolt. And we can use the formula of the gain to calculate it, and we will get 17. The gain is 79, and we convert to dB is 37.96 dB. And we continue increasing the input frequency, and when the input frequency is over to 10 kHz, when we can see that our output will be decreasing because the gain also decreasing, sweeping. And this is the compare table for the comparison result. And the first table is for the comparison result for the theoretical result and the simulation result. You can see that the percentage error for the mid gain between theoretical result and the simulation result is 0.11%, and the low cutoff frequency is 11.5%, and the high cutoff frequency, the percentage error is 9.5%. And the second table is for the comparison between theoretical result and the experimental result. And we can see that the percentage error for the mid gain between theoretical result and the experimental result is 0.626%, and low cutoff frequency is 8.3%, and the high cutoff frequency is 8.2%. That's all for me. Thank you.
So this is the discussion of our group project. The experiment for this circuit is designed by Proteus that we are already designed and simulate. After the simulation has been running, we are proceed to the lab for the testing result. At the lab testing, we start to test the output of our circuit. We connect channel 1 to the input of our circuit and connect channel 2 to the output for our circuit with the probe. Because we use our frequency between 1K and 10K based on the theory and calculations, will get gain around 80. So if we make our input frequency higher than 10 kHz, we observe that our output voltage is decreased. This is because the gain is decreasing at the frequency response graph. On simulation, when the input frequency is over 10 kHz, which is the high cut-off frequency. When the frequency is less than 1 kHz, we can observe that the output is increasing if we increase the input frequency from 10 Hz to 1 kHz. This is because the gain wheel is increasing when the input frequency is increased from 0 Hz to 1 kilohertz. So the last part is conclusion. The conclusion is overall of our project members got. So in conclusion, we can observe that before like input frequency reach to the low cut-off frequency, the output voltage of the circuit will be increased. When the gain will also increase, when the frequency is between the low cut-off frequency and the high cut frequency, the output voltage and the gain of the circuit will stop increasing because the band pass filter pass all frequencies between two critical frequency and reject other frequencies. So after the input frequency is reached to the high cut-off frequency, the output voltage of the circuit will be decreased. When the gain will also decrease, we can also that the result between theoretical simulation and experimental is different. So that's all for our group project presentation. Thank you.